You guys learned about Pythagorean theorem in a previous class, right? It's a way you can find missing sides in a right triangle. Right? That's what this says, that you can use Pythagorean theorem to find missing dimensions for your right triangles. Anybody remember what the formula for it is? Yeah? So we got a squared plus b squared equals c squared, where a and b are supposed to be the two shorter sides, while c is the hypotenuse, right? C is always the one directly across from the 90-degree angle, okay? All right, so we are going to fill in this chart looking at these figures. So let's see, on figure number 1, what is our short leg? 3, good. Okay, and what is our long leg? 4. And we can use Pythagorean theorem to find the hypotenuse, right? So the theorem would be a squared. Well, what would our short leg squared give us? 9 plus 16 equals c squared. Right. But we don't want c squared, we want just c, right? So what would I need to do to the square? Yes, take the square root. So, like he said, this is 25, so I would need to take the square root of our sides, right? So we end up with our hypotenuse should be 5. Very good. Okay. All right, so then let's look at figure 2. Well, what sides did they give us on figure 2? Right, hypotenuse and short leg. So I'm going to go ahead and plug those into their boxes. So there's my short leg, hypotenuse is over here, right? Okay, now I should still be able to use Pythagorean theorem, just manipulate it in another way so that I could get the long leg, right? Okay, so the long leg is b squared, so I basically would want to try and get b squared by itself, right? So that would mean I would have to move the a squared to the other side, and how would I do that? Exactly. Okay, so now underneath my square root, like she said, we're going to have c squared minus a squared. Well, if our c is 13, what's 13 squared? Minus, what's our a squared? 25. And what is 169 minus 25?
144 in the square root.
And the square root would be 12. Very good. So, our long leg would be 12. All right. So, basically, you can manipulate the formula for whatever seems to be missing, right? Okay, so let's do it for figure 3. So, if I'm looking at figure 3 there, what sides do they give us? So I'm going to go ahead and plug those into their boxes. Okay, and so it's just like what we did on number 2, right? So underneath my square root, I should have my c squared. So for us, c squared would be, and then minus 49. There we go. Okay. Now what is 625 minus the 49 going to leave us with?
24.
Yeah, and then the square root would be
24.
There we go. All right. What about figure 4? What did they give us on that one? Okay. But it still should work the same way as what we did on 2 and 3, right? We just are subtracting this one from the hypotenuse. So what is 17 squared? Okay, so I got underneath my square root 289 minus what's 15 squared, right? So what do we get when we subtract those?
64.
And the square root of 64 is, there we go. Okay, on number 5, what sides did they give us?
Long leg and short leg.
Right. So this one's more like the first one we did, right? So underneath my radical, I got 9 squared, which is plus 40 squared, which is
1,600.
good. And if we add those together and take their square root, we end up with
41.
Good. Okay, last one, number 6. What sides did they give us? Okay, so we got 60 and 61. So how can I find the short leg? Okay, what is 61 squared? Okay, minus what, 60 squared? 36. Okay, and that's all underneath our radical. So once we subtract and take the square root, we get
11.
right. The square root of 121 is 11. All right. So no matter what side is missing, if it's a right triangle, we can use our Pythagorean theorem to manipulate it in some way to find the missing side. Right? Okay. Then down here, it says each set of numbers below has a common factor. Find that factor and factor it out of your set so that you can determine which common Pythagorean triple that those 3 sides make. Okay? So, some of the common ones are the ones we already dealt with over here. These are ones that it may be worth memorizing because if you have them memorized, it cuts out a whole step of having to do Pythagorean theorem for whatever it is you're going to have to do next. Okay? All right, so on number 7, what is your greatest common factor there? What can you factor out of all 3 of those? 4, yeah. So I am going to do that. I'm going to divide all 3 of these by 4. So on number 7, common factor was 4. Well, when I divide 20 by 4, what are we going to get? 5. Okay, 48 divided by 4. And 52 divided by 4. Very good. So 5, 12, 13 is one of the very common Pythagorean triples that you will see. If you have it memorized, you won't have to do Pythagorean theorem to find the missing side. All right, number 8. What's my GCF there? 2. Okay, so if I divide all 3 of these numbers by 2, what sides are we left with? 3, 4, and 5. Very good. Also another very common Pythagorean triple. Okay, number 9, what's our greatest common factor? 3, okay. So if I divide all of those by 3, what are we left with?
9, 40, 41.
Good.
Whoa!
All right, and then in the last one, what all those have in common? So I'm going to divide all of these by the square root of 3. Right, because we treat a square root kind of like a variable. If this was 7x divided by x, the x's would just cancel out for our answer, right? So the same thing's going to happen here with your square root of 3. So we are left with just the whole numbers in front.
So they could give us a triangle and like the sides could be labeled as like 7 squared 3.
Mm-hmm.
And if they were all the same, then you would just get 7 squared 1.
Okay. Last section on this page. It says, without using Pythagorean theorem to find the missing side, they want you to figure out what the missing dimension is. Hint, you may need to pull out some common factor. Guys. So on number 11, is there a common factor to pull out between 8 and 17? No. But if we look back up at our chart there at the top, what do we already know should go in the blank? 15, right. 8, 15, 17 is one of the common Pythagorean triples. Okay? What about number 12? Any common factor between 5 and 13 to factor out? No. So what do we already know numbers should go in the blank? 12, right. It's one of our common Pythagorean triples.
So they don't have to like go in the same order.
What do you mean?
Well, this one is 4, then like they're doing then 12, but up there it says 5, 12, 13.
Right here?
Yeah.
5, 12, 13, 5, 12, 13.
Oh, I did the wrong one. My bad.
All right, and then number 13. What's our GCF there? 6, okay. So I'm going to factor out a 6 from both of the terms that we have. That would leave me with 3, a blank, and 5, right? So it's got to be 4, right? That's what goes in the blank here. So what would it have been before we factored out a 6?
24.
Okay. Okay. So again, if you have your common Pythagorean triples memorized, you could still figure out what it is, even if they are the same thing on a larger scale, just by pulling out a GCF. All right, number 14. Okay, obviously 5 over 2, not going to be one of our commons, right? So how could I get rid of the divided by 2 there? Multiply by 2. So that's what I'm going to do to each term, times 2. Okay, so 4 times 2 would give us 15 over 2 times 2 would just be 15. And then we have a blank. Right. Okay. Now, this was before, or this is after, sorry, that we multiplied by 2, right? So if I wanted to put that in the blank before, so yes, we could either leave it as decimal or put it as a fraction like they did with the 15 over 2, so this would just be 17. Okay, last one. What's our GCF on number 15? Okay, so I'm going to divide both of these by 10, which would give us, so what should go in the blank there? 41, but that was after we divided it by 10, so to put it in the blank above, 10. Okay?
Question.
So, now that we've reviewed Pythagorean theorem, we're going to talk about the converse of Pythagorean theorem. Okay, so we know that Pythagorean theorem works for all right triangles, right? All the ones that have 90-degree angles. Okay, we're going to talk about how you can also use this theorem to determine what kind of triangle you have. Okay, so we know which parts are supposed to be A, B, and C, right? If we're given 3 numbers, the hypotenuse should be the longest, and then you have a short leg and a long leg, right? So let's just fill in the numbers for our columns here. So with 5, 6, 7, which one is my C?
7.
The 7, okay. It says in this box to put C squared, so for us that would be, okay. All right, and then A, we know is supposed to be the smaller or shorter leg. So for us, that would be, and 5 squared would be,
25.
okay, and what's our B squared going to be? 36. Okay, the next column just says to add your A squared and B squared. For us, that would be 61. This last column is what we haven't figured out yet. It says that this should be able to help us determine if we have an obtuse, acute, or right triangle. Okay, so let's go ahead, fill in the rest of our chart so we can make some comparisons between the numbers. So for 3, 4, 5, what's my hypotenuse? All right, so what is my hypotenuse squared going to be? 25. All right, and what is our A squared going to be? And our B squared? 16. Good. Okay, and what is our A squared plus B squared going to give us? 25. Okay. All right, for 8, 9, and 13, what's my C squared? Okay, what's my A squared? And my B squared? And what do I get when I add those two? Good. All right, and then last one, what's my C squared? All right, and my A squared? And my B squared? And when we add them together? Okay. All right, so we noticed some of them, the c squared and the last number ended up being the same, right? We had a couple that turned out that way, right? Which basically means when I added a squared and b squared, it equaled c squared, right? Which we already knew, right? That's what Pythagorean theorem says. So that's what they said right here on number 1. If your a squared plus b squared equals c squared, then you know you have what kind of a triangle? A right. Okay, so if it says equal, right? If they ended up equaling each other, this means I must have a right triangle. Okay, so which ones did that happen for us?
3/4 of 35.
Good. So I can fill that in my box over here. And both of those are one of the common ones that we talked about on the other page, right? So our common Pythagorean triples. Okay, so now we just need to determine which one is going to tell us if it's obtuse or acute, right? Okay, so if your c squared is not equal to a squared plus b squared, if your c squared is less than what you get when you add the other two together, then you have an acute triangle. Okay, which would mean in reverse, if it's greater than, we must have what kind of a triangle? Right. Okay, so if I go back up to my chart here, I'm supposed to be comparing c squared, which is this blank here, to a squared plus b squared. So for my 5, 6, 7, which was greater, c or a plus b?
A plus B.
A plus b. So c squared was less than a squared plus b squared. This one must be
Acute.
acute. Okay. All right, for our 8, 9, 13, here's my c squared. Is it less than or greater than the a squared plus b squared?
Greater than.
Greater than, so it must be right. Okay, so we can use this idea right here to determine what kind of a triangle we have. If it is equal, we have a right. If c is less than, it's acute. If c is greater than, it's obtuse. Okay.